So we finished now our discussion of classical physics. We've left out some topics and whatnot. It's by no means complete, but we have certain objectives for our physics, and here we are, at the end of everything we've done, to talk about a type of motion that we haven't really considered before, and that is oscillatory motion. Now, oscillatory motion is a class of periodic motion. And periodic motion I understand because I've already solved problems of an object going around in circular motion. One of the characteristics of circular motion is that it's motion that repeats itself in time. Going around a circle, there's a certain circumference, and so I define a time period of that motion, and naturally a frequency associated with that motion. As we talked about the rotation of things, instead of the translational frequency, we started talking about the angular frequency omega, the frequency of rotation through an angle. So there's concepts of periodicity that we're already very familiar with. But there's a type of motion associated with a particular kind of force and a particular kind of energy that we find pervades all of science and engineering. So that's the type of motion. Now, I'm going to start with the simplest possible example that we have. It's called the mass on a spring problem. Now, a mass on a spring is not a terribly useful problem because all I'm going to do is attach a mass to a spring, pull it from its equilibrium position and allow it to oscillate back and forth, a sort of vibrational, springy type of motion. And that's not terribly practical because I don't see that applied anywhere in everyday science or engineering. However, the mass on a spring is the example case of this particular kind of motion that can be used to describe and explain all other kinds of oscillatory motion. That is, it's the benchmark case of this motion. It's how we describe it. So what I'm going to do here is I'm going to give myself a solid barrier that doesn't move. So I'm drawing here sort of cartoonish, a barrier. And to that barrier I connect a spring. Now I already know something about the forces exerted by springs because I've already investigated the spring force and the spring potential energy. So let me say that this spring is a spring constant K associated with it. I'm going to attach to it a mass. Notice that I haven't drawn any surface that the mass is sitting on where there might be some friction or whatnot. This mass is entirely horizontal with no other interactions. It's not because I couldn't include those interactions and have a good time doing some fun physics. It's just that I want the purity of this mass moving solely under the influence of a spring force. So here's the mass M and it's attached to a spring. And there it rests at a position where the spring is not stretched or compressed from its equilibrium position. That is, I'm claiming, as I've drawn it here on the board, this is a condition under which the spring exerts zero force on the mass. And so if I just let it go at t is equal to 0 in this configuration, it will sit there at rest in equilibrium. Therefore, we call this the equilibrium position. It's very common to set the equilibrium position to be the zero position. So for my choice of coordinates, I'll choose 0 to be at the equilibrium position of the system, and I'll choose to the right to be positive, quite arbitrarily, but I'll choose to the right to be positive. Now what I'm going to do in order to get some action that I'd like to analyze is that I'm going to draw the mass M away from its equilibrium position. I'm going to stretch it this way a little bit on the spring, and I'm going to stretch it to a position that I'm going to call A. The reason why I call that position A will become apparent momentarily. But I'm going to stretch it to a final position that I call A, and I'm going to release it from rest. Now when I release it from this position A, it is subject to a spring force. Pulling it to the right has stretched the spring. Now the spring exerts a restorative force, so the force exerted by the spring is naturally directed to the left. And so that force is going to draw the mass to the left. And so from A, it will proceed to the equilibrium position. When it gets to the equilibrium position, it will have a velocity because the spring will have done work on the mass to give it a kinetic energy. So when it reaches 0, it will not then return to rest, but will go right through 0, proceeding then to the left, compressing the spring. Now, when the spring gets compressed, the spring, exerting a restoring force to the right, will begin to slow the mass until it comes to rest again. Now, a little bit later on in the discussion, we'll talk specifically about the conservation of energy, but I know that the spring is an elastic force, energy is conserved, and so I would not be surprised to find that the mass will go through 0 and arrive here at a position negative A, compressing the spring over here. So it's sort of symmetric around 0. Once it comes to rest at negative A, the spring force is not 0. The spring force is, in fact, maximal and directed to the right. And therefore it will push the mass again to the right. Well, it will arrive at the origin, but it'll have a velocity. Travel through the origin until it stretches the spring arresting its motion until it comes to rest. And you see what happens now. It oscillates under the influence of the spring. And because I have not in this description including any dissipated forces like viscous drag or force of friction between the block and some surface, it will oscillate this way forever with the energy as a conserved quantity, with its velocity changing direction, becoming positive and negative, increasing and decreasing in magnitude as it moves through the oscillatory motion. So this motion, quite complicated. What I would like to do is for motion of this kind, oscillatory motion, I would like to find the position, velocity, and acceleration. So it's very nostalgic. What have I been doing this whole time? I have Newton's second law. Using Newton's second law, I can find the acceleration. I integrate the acceleration twice, I get velocity, I get position. That's the whole game, is to describe the motion of physical systems based on the constraints or conditions that affect the motion. Well, here, the constraint or condition that affects the motion is something a little bit new. It's a spring causing oscillatory motion. But my approach is identically the same. What should I do in the next moment? I should draw a free body diagram that describes the motion. And so I'll draw here a free body diagram for the mass showing all of the forces which act on the mass. Well, I'm restricting this analysis to the most general, most simple type of analysis that I can. The only force that acts is a force of, in the initial case that I've drawn it, where I've drawn the mass away from equilibrium to the position positive A, that is drawing the mass to the right in the diagram, is a spring force exerted by a spring which is directed to the left on the free body diagram. And that's it, one force. One force, what harm could there be? There's one force. I've drawn a free body diagram. Now I'll write Newton's second law for the system. Well, Newton's second law dictates that the sum of all of the forces that act on the mass will be equal to the mass multiplied by the mass's acceleration. Now I'm going to jazz this up a little bit because we know that the acceleration by definition is equal to the rate of change of the velocity. So I'll replace the acceleration in my equation with dv dt, the acceleration as I know it. And just recently, I've been doing some derivations where I used a happy notation where I used a dot to indicate a time derivative. Well, in order to get the acceleration, I have to take two time derivatives of position. If I know the position is a function of time, I take one derivative, gets me the velocity. A second derivative gets me the acceleration. And so I can write this as mx double dot. X double dot is the acceleration because I have to take x and take two time derivatives, two dots. That's the acceleration. So now that I've dealt with the right-hand side there, and I have it the way that I like it, on the left-hand side, I'll address the net force. Well, I have a force directed to the left, so I'll give it a negative sign. And it's the force exerted by a spring. Well, I know the force exerted by a spring is a linear force, or at least approximately so, according to Hooke's law. It turns out to be true that if I take a coiled bit of wire that we all recognize as a spring, if I take a coiled bit of wire and I stretch it, the force increases linearly with the stretch. But there's a limit to that. It's not perfectly that way. If I really stretch the bejesus out of a spring, I'm going to get some nonlinear behavior out of it further and further I go. But for small bits of stretch, the behavior of the spring is certainly approximately linear, and we're accustomed to saying that the spring force is K times X, which would be equal to M X double dot. And I hope that you see immediately why I'm using the X double dot notation for the acceleration. This is an equation that relates a function of time to its derivatives. In this case in particular, X, which is a function of time, the position changes as a function of time, that's what I'm interested in, is being related to the second derivative of the position with respect to time. This is a differential equation. It is a differential equation. And so it requires a new technique to solve. Now, recall in the past that we've had differential equations to solve. For example, when we studied viscous drag. I wrote Newton's second law for viscous drag and realized suddenly that it was a relationship among the derivative of a relationship among the velocity and the derivative of the velocity. And so I had to separate the variables and integrate both sides of the equation. And that's how I got my solution to the differential equation. You'll find here that I'm going to take a very different technique. But before I get about solving it, I'm going to write it in its traditional form by adding kx to the other side of the equation so that I have m x double dot plus kx is equal to 0. And obviously I haven't changed it at all. I've just rearranged some quantities. What I'm doing here is purely traditional. So I'm going to divide through by the mass so that my final differential equation that I'm going to consider here is x double dot plus k over mx is equal to 0. This is called the harmonic oscillator differential equation. And it is a differential equation of such great importance to science and engineering that you should, this is like the essential of all essentials. You should recognize it immediately, and you should know what its solutions are immediately. It is the language of so many applications in science and engineering. I can't undersell that. The harmonic oscillator differential equation is of critical importance. It's a differential equation that you want to know how to solve readily. So now the question, how do I solve this differential equation? You might actually enjoy the answer. The way that I'm going to go about solving this differential equation is I'm going to guess what the answer is. Well, you can imagine that my guess is going to be a fairly good guess, but I'll have to test it to convince you that it's so. The way that I'll make my guess is I'm going to make a graph of the position as a function of time. I'm going to look at what that graph looks like and see if maybe the graph gives me some insight as to what I should choose. I'll start making my graph. Notice the graph is a function of time. I'll start making my graph at t is equal to 0. Well, I know the position at t is equal to 0. The position at t is equal to 0 is A. That's where it starts out at t is equal to 0. It has a positive position A. I know later on in the motion, by the way, that it'll end up down here at negative A at some point. I know that that in fact happens, so I'll just mark that on the vertical axis of my graph, the x-axis. So it's going to go between A and, well, what happens then? It starts out at A with a velocity of 0 because I release it at rest. And so the slope of the graph at t is equal to 0 should be 0, should be horizontal then. And then it goes to the left, which means it must have a negative velocity, which means the slope must become negative. And then it passes through equilibrium. So what I expect to happen is I expect it to go like this. But it has a velocity when it reaches equilibrium, so it will continue to the negative position here, where it finally comes to rest again. That is, the slope should become 0 when it comes to rest there. So it looks like that. And if I follow along with this reasoning, again, returning to the equilibrium position, what I'm going to discover is that the graph looks like this. So I have a really good suspicion for my guess. My guess for the solution is that the position as a function of time is likely the constant position A multiplied by a cosine, because this graph that I've drawn reminds me of a cosine function, doesn't it? Cosine of what? It's a function of time. It's a function of time. It's not a function of angle. It's a function of time. So what should I write on the cosine? Well, it's some function of time. I have to write a constant, omega, times t. I've just written in a constant. I could have written alpha, could have written a smiley face. I wrote an omega. And you say, well, that's a little dangerous there because omega already stands for something. Well, I have a little pre-knowledge of what's happening, so it's all going to work out for me. It's all going to work out for me. This is my guess. I imagine that the solution to this differential equation is a cosine function, which is known as a harmonic function. Sines and cosines are called the harmonic functions. I told you in some math course. Sines and cosines are called the harmonic function. That's why this is called the harmonic oscillator differential equation. I guess that's the answer. But in order to be sure if this is the answer or not, what I have to do is plug it into the differential equation and see if it satisfies this equation. That is, in this equation, wherever I see an x, I have to put an a cosine omega t. And in this equation, wherever I see x double dot, I have to put the second derivative of that. So clearly, a thing that I have to do now is I have to take derivatives. Successive derivatives of the position as a function of time. So this is the velocity as a function of time here is equal to the derivative of a cosine omega t. A is not a function of time. It's constant. But the argument of the cosine is a function of time. So what I'm going to do is a little bit of chain rule. I'm going to take the derivative of the cosine, and then I'm going to multiply by the derivative of the argument of the cosine. That is multiplying by the derivative of omega t. Derivative of cosine is negative sine. The derivative of cosine is negative sine. And so this derivative is negative a omega sine omega times t. But that's just the first derivative. In order to test my guess, I need the second derivative. And so I'm going to take another derivative of this, which will give me the acceleration of my harmonic oscillator as a function of time, and I'll take the derivative of this. Well, the derivative of sine is cosine. So this negative sign out in front is going to persist. The derivative of sine is cosine, and I'm once again going to get a factor of omega out in front. So what I get is negative a omega squared cosine omega t. That is what the acceleration as a function of time is. That is what x double dot is. So now it's time to test it out by plugging it into the harmonic oscillator differential equation and see what I get. So let's take this over to here, see what happens. First thing I start off with is x double dot, that is negative a omega squared cosine omega t plus k over m times x. Well, x is a cosine omega t, and that must be equal to 0. Well, look what happens. A lot of really great stuff happens. Right? This equation is true. Well, before I state that, let me look here. I have a cosine omega t and a cosine omega t, and they cancel. That is, I can divide through by cosine omega t because I have 0 on the right-hand side. And I have an a here that goes away because I'll divide through by a, and I have 0 on that side. So what am I left with? What I'm left with is negative omega squared plus k over m is equal to 0. So it is entirely possible, and in fact it turns out to be true, that this solution solves the differential equation, but there's a condition. The condition of this solution is that I must choose omega to be equal to the square root of k over m. There's a relationship that you're going to use over and over and over again in problem solving. That omega is equal to the square root of k over m. If I select omega that way, then yes, a cosine omega t is in fact the solution of this differential equation, and the motion of the oscillator is in fact cosine, and the velocity of the oscillator is in fact a sine, and the acceleration is in fact a cosine, according to these choices that I've made here. I chose to call this constant omega because indeed it is the angular frequency of the motion. It is the angular frequency of the motion. That's why I used omega as the symbol. It's strange a little bit, I think, in the mind of the student, that if I observe this motion, it's going to be side-to-side motion like this, oscillating side to side. How does that motion have an angular frequency? How does that motion have an angular frequency? Well, think about it like this. Imagine that I have a circle, and this is the x-axis along the circle. And the circle happens to have a radius a. So if I put the origin at the center of the circle, then this side of the circle is a, and this side of the circle over here is negative a. Change my case, pardon me, is negative a. Now, imagine that a particle goes around in circular motion with constant velocity around this circle. I describe its position with a vector drawn from the origin to its position here on the circle, call that r. And I describe its position with an angle theta, something that very recently we're quite familiar with, this approach to describing the motion. What is the x component of that motion? What is the x component of that motion? Well, the x component is clearly equal to a times the cosine of theta. A times the cosine of theta. Clearly, the x component is r, which is equal to a, times the cosine of theta. In fact, that's how I should have written it. I should have written it. You know what I'm going to do? I'm going to make a change right here in the middle, just so it finishes up. I wasn't very careful with the way I did that. X is clearly equal to r times the cosine of theta, as I've stated, right? It's r times the cosine of theta. But r is the radius of the circle, which is equal to a. So x is clearly equal to a times the cosine of theta. But what is theta equal to? Well, as the mass goes around at constant speed, I might consider that its angular position theta is equal to theta naught plus omega t plus 1/2 the angular acceleration times t squared. Well, it's going around at constant angular speed, so that acceleration is equal to 0. I can choose the initial angle to be equal to 0. That's entirely up to me. So theta is equal to the angular speed, the angular frequency, same quantity. And so I make that replacement, so x is equal to a times the cosine of omega t. Sometimes you'll see this described as the harmonic motion is if I had a light source from above here shining down on this mass as it went around in circular motion, and the harmonic motion was the shadow moving back and forth between plus a and negative a. I've been ignoring a and negative a up until this moment. That is, of course, what we refer to as the amplitude of the motion. I've called it capital A because it's the amplitude of the motion. I think our text that's for this course might call it x sub n, or x sub m, pardon me, for the maximum position. I'm not wild about that particular notation, so I'm going to use capital A for it, which, you know, is the way I was raised. So, anytime I see the harmonic oscillator differential equation, anytime I see the harmonic oscillator differential equation, I immediately know what form the solutions are going to take. They take this form. And being very early to this material, you might say, well, Shai, that's great, but how many times am I going to encounter a mass on a spring? Now, you've shown me a mass on a spring, and so I can solve that problem. Well, good for me. What good does that do me? Well, it turns out once you solve the mass on a spring problem, you can solve a fantastic number of oscillating problems. Remember, the mass on a spring is just an example. The mass on a spring is just an example of oscillatory motion. It's the test case example, the example that we talk about everything in context of. It is very similar to bungee type motion. That is the motion of a vertical spring. And you're sort of showing a little prescient knowledge of what's going to happen because that problem of a mass on a spring vertically, or in the case of a bungee cord, an elastic cord, which has spring-like property. That's a problem that I will solve, an important problem. Yes. I have assumed, that's a fantastic question, thank you. I have assumed the conservation of energy the whole time. And you might say, well, Charlie, I want to see it with some viscous drag in there. And then you immediately think, oh, wait, no, I don't. Because I don't want to have to solve that problem. I will solve that problem for you. But it turns out that's the last problem that you solve, is throwing in viscous drag. So here's what I want to point out. The importance of this, the critical importance from this, comes from a very, very important principle. And that is, I'm going to state the principle, and then I'm going to sort of demonstrate it mathematically. Wow. I'm going to demonstrate it with mathematical argument. This is happening because the spring force is Kx. If the spring force had a different mathematical behavior, if the spring force had a different mathematical form, the differential equation would be different. These would not be the solutions. These would not be the solutions. So you get harmonic oscillation in situations where the spring force is linear. That's when you get harmonic oscillation. A linear force leads to harmonic oscillation. Well, a linear force implies, I'm not sure where I'm going to write this, a linear force implies a potential energy which is equal to 1/2 kx squared. So if I want harmonic oscillation, the spring force has to be of a kx type. It has to have that dependence. And if I want harmonic oscillation, the energy has to be a 1/2 kx squared type of energy. There are a lot of different energy that are not 1/2 kx squared. For example, consider this potential energy function that I am making up off the top of my head. The potential energy as a function of x, and it looks like this. That's just an arbitrary squiggle that I drew. That is an arbitrary squiggle that I drew. That is not 1/kx squared, or sorry, 1/2, it's not 1/2 kx squared potential. It's not. Its potential is a function of x, but it's sure not that. So it's not harmonic oscillation. Think about how the derivative of the potential is equal to the force. A particle moving in this potential is getting shoved around all over the place as the slope of the potential energy changes from this and that. It gets steeper, positive, negative, shallower. It gets wiggles all over the place. Consider, though, this position right here, which happens to be the location. I'll label it x0. It happens to be the location of a potential energy minimum. Look at that particular location on the graph and do not allow yourself to be distracted by the rest of the graph. Isn't it kind of like a parabola there? Like a parabola kind of fits in there. Parabola kind of fits in there. Yeah, but outside it's all wet. No, ignore that. Let's say I want to describe the motion of the thing. I don't let it get too far away from that position, x0. I don't let it get too far away. I'm not going to let it stray that far. Well, how are you going to stop it? Energy. I'll keep the energy low enough that it can't get away. Because remember, the total energy drawn across that graph is going to determine the turning points of the motion. So I'll keep it there in that little minimum. What would that be like? Well, you say you're pulling a trick on us because you deliberately drew it in such a way that it looks like a parabola. No. I mean, I kind of did. But it's not a requirement. Some of you have reached a point in your mathematical training where you have encountered a thing that's known as a Taylor series expansion. Any potential energy function as a function of x can be expanded in a Taylor series. I want to show you what happens. Consider this potential energy as a function of x. Where am I going to write it? I'm going to write low. I hate that. Potential energy as a function of x. I'm going to write a Taylor series expansion of it by approximation. I'm going to write a Taylor series expansion of it as an approximation of that value. The Taylor series expansion of this function, like how the Taylor series is defined, is the potential evaluated at x0. That's the first term in the series. So when I say the Taylor series expansion of u, this is, I guess I should put like a little warning on here that it's in the vicinity of x0. So the Taylor series expansion of the potential energy function u as a function of x in the vicinity of x0 is equal to the potential energy at x0 plus the first derivative of the potential energy evaluated at x0 times x plus 1/2 of the second derivative of the potential energy evaluated at x0 times x squared plus 1/3 the third derivative of the potential energy evaluated at x0 x cubed. Now, I can keep going with this, right? It's the nature of series. I can keep going with this on and on and on. Just keep going on and on and on with it. More and more terms, higher and higher order. But I want to evaluate these terms that I have in front of me right now. The potential energy evaluated at x. I choose where 0 is. I choose. So I'm going to say that this potential energy, where that minimum is in the vicinity of x0, I'm going to choose that potential energy is equal to 0. So that is 0. I choose. Isn't the first derivative of the potential energy the slope of the potential energy? Isn't the first derivative the slope? What's the slope at x naught? 0. The second term is 0. It might be bothering you. Rightly it should. All this is only true if you stay near x naught. Okay, I'm near x naught, which means x minus x naught, that is the difference between the two, that is how far I stray, x, is small. If x is small, then x cubed is certainly small. Cube a small number, you get smaller. Look what I'm left with. 1/2 a constant value times x squared. The message here is every potential energy function ever that has a potential energy minimum is approximately harmonic oscillator as long as you stay near the equilibrium. For small oscillations, if you stay near the equilibrium, every potential energy minimum is harmonic, which means for small oscillations, every oscillation that happens in every physical system in the universe is harmonic oscillator, which makes this some really, really important physics. This assumption, you'll find, right, for small oscillation. We're going to make this assumption very, very often in problem solving. We're going to say, no, the potential energy is not harmonic. It's not harmonic, but it's very close. It's not harmonic, it's very close. An example, right off the top of my head, to speak of, a potential energy function that we're familiar with. Consider the potential energy associated with planetary motion, which we recently discussed. That is not 1/2 kx squared, that potential. That's not 1/2 kx squared. In fact, that's proportional sort of r squared minus 1/r potential. That's not harmonic oscillator. But the orbit of the Earth is nearly circular. That is, the total mechanical energy of the Earth's orbit around the sun is very nearly equal to the minimum potential energy of the orbit. That means where the total mechanical energy intersects the potential energy here keeps the Earth in its orbit around the sun very close to equilibrium. Is the aphelion, perihelion motion of the Earth along that radial vector, is it harmonic oscillation? Absolutely. In approximation, harmonic oscillation. It goes as the, right? That's just one quick view of an application of harmonic oscillation to a situation that's more sophisticated. In the very next lecture, I'm going to give you a slew of examples of harmonic oscillation where I make this approximation. Really, really stunning, Blake. Yes, that's the message, Blake. When I have a system that I identify as having the harmonic oscillator differential equation, the solutions are always of the form A cosine omega t. Now, I might name the constants different depending on the nature of the physics that I'm doing. It might not always be A, it may not always be omega, but it always has the mathematical form A cosine omega t. If there's a mantra to our course, a serious mantra anyway, it would be that most problems are best solved from the point of view of energy. Most problems are best solved from the point of view of energy. So I'd like to consider the energy of a harmonic oscillator, because as the oscillator goes through its motion, the mass in the harmonic oscillator has kinetic energy. And since the speed is continually changing, the kinetic energy of the oscillator is continually changing. Makes sense. Also, the spring is being stretched from its equilibrium position, and so it has spring potential energy according to the stretch, according to 1/2 kx squared. So the total energy of a harmonic oscillator will naturally be the kinetic energy that it has at any instant in time, 1/2 m times the speed squared, plus the spring potential energy that it has, 1/2 k times x squared, that it has at any instant in time. And so very, very simple to write the total mechanical energy of a harmonic oscillator this way. But of course, this is always changing in terms of the proportion that is kinetic energy and the proportion that is potential energy. When the oscillator is going through the equilibrium position, its spring potential energy is 0 and its velocity is maximum. The energy of the oscillator is entirely kinetic energy. When the oscillator is at the fullest extent of the motion, it for an instant comes to rest and the spring is stretched maximally. Therefore, the energy is entirely spring energy and there is no kinetic energy. So what's going on during the oscillatory motion is the energy is being exchanged back and forth between the spring form and the kinetic form. Back and forth, back and forth. Well, I'm going to make some substitutions here in order to write a final expression for the total mechanical energy. Recall that the velocity as a function of time for harmonic motion is equal to negative a times omega sine omega t. I just made that argument as I was solving the differential equation for harmonic oscillation. This constant out in front, make a little aside here. Since the sine function goes between +1 and -1, this constant out in front, a omega, is the maximum value of the velocity. It's the velocity as the particle goes through equilibrium. Now, there's a negative sign out in front. But for part of the cycle, the sign function is negative. For another part of the cycle, it's positive. So ignore the negative sign. The magnitude of A omega is the maximum speed that it has as it goes through the equilibrium the first time and goes through the equilibrium on the return. So A sine omega t. In order to plug it into the equation above, naturally what I want is v squared. So I'll go ahead and square this thing, which is going to be A squared, omega squared, sine squared, omega t. Simple enough to do. In a moment, I'm going to make that substitution. X squared, I can easily compute because I know that for harmonic oscillation, x is equal to A times the cosine of omega t. Notice that A is the maximum extent because the cosine goes between positive 1 and negative 1. The amplitude is the maximum extent. Of course, I already knew that. And so x squared is simply this squared, which would be A squared cosine squared omega t. I'm going to make the substitution of v squared and x squared into my expression for the total mechanical energy. So what I have is 1/2 m times the speed squared, which is A squared omega squared sine squared omega t, plus the potential energy, 1/2 k x squared, with my substitution for what x squared is equal to, which is A squared cosine squared omega t. Now, I see a sine squared and a cosine squared in the neighborhood of each other and being added. I'm definitely looking for something special. Yeah, the velocity is a function of time. If the initial position is, at t is equal to 0, the initial velocity is negative because, okay, good. So this is the total mechanical energy is equal to, look what's going on here, I have an omega squared. Recall that in order for all of this to be true, omega has to be equal to the square root of k over m, which means omega squared is equal to k divided by m, which means omega squared is k over m, the m cancels, it's a squared times k. Notice it's the same, ka squared, and so what I have is that 1/2 k a squared factored out. And then I have sine squared omega t plus cosine squared omega t, which of course is equal to 1. And so the total mechanical energy of a harmonic oscillator, I find, is 1/2 the spring constant times the amplitude squared. So the total mechanical energy of any oscillator, which at any instant in time is some combination of kinetic and potential energy, that total mechanical energy is always 1/2 k times the amplitude squared. That's the total mechanical energy of a harmonic oscillator, worth knowing. Now, in the few minutes that I have remaining here, I want to make sure that I accomplish all of my goals, and a very important goal that I had for today was to talk about what Blake had just mentioned, and that is an oscillator arranged vertically. Because so I'll solve that problem right now. So here I have a support, but instead of doing my support horizontally, I do the support vertically. So here's a spring hanging vertically with the mass connected underneath. So here's a mass M. Perhaps the same apparatus, same mass, same spring, but now I've arranged it vertically. And I've got a little bit of a snag here. Because when I go to solve the problem and I write my, draw a free body diagram here, yes, as the mass descends, the spring force directed upward, no problem, there's a spring force, Fs, the force exerted by the spring. And I like that it's there because it's spring that causes the oscillatory motion. That's just fine. However, that's now not the only force acting on the mass. There is also a weight force, mg, directed downward. So when I write the differential equation for this system, which will obviously oscillate, when I release this, it's going to bounce up and down in oscillatory motion. When I write the differential equation, taking downward to be the positive direction, I'll write mg minus kx is equal to mx double dot. Rearranging this in the traditional fashion, x double dot plus k over mx is equal to not 0, but g. That is not the harmonic oscillator differential equation. That is not the harmonic oscillator differential equation. So I've got a little bit of a problem that I need to figure out. It turns out the answer is beautiful and simple and lovely, and it is this. Consider that this mass hanging here motionless on the spring is not the equilibrium position of the spring. Consider, if I take the mass off, the spring will hang at its unstretched length. It'll hang there unstretched. When I add the mass to the spring, it will stretch the spring down to a new force equilibrium position. That new force equilibrium position is easy to figure out. It's going to be when the force exerted by the spring upward is equal to the weight of the mass downward, such that kx is equal to, I'm going to call it kx prime, if you don't mind. That is how far it gets stretched. Right? I'm going to call that kx prime. Kx prime is equal to mg. And then I'll solve for x prime. How far it gets stretched is mg divided by k. This is a procedure that we already did on an exam earlier when a block was set upon a spring and compressed, and we used that information in order to determine the spring constant. Now here doing it slightly differently. So what I'm describing here is that this mass, when it's hung on, stretches the spring down to this new position, which is not 0. It's not the unstretched length, but is in fact x prime, the distance it's stretched to. What I'm going to do is I'm going to choose to change the coordinate system. Instead of using 0 as the unstretched length of the spring, I'll call 0 where x prime is, such that, I'll say this is the new equilibrium position, such that when I take the mass m and I bring it down even further, that is, I pull it down from that and then I let it go, it's going to oscillate. I pull it further down. It's now at a new position, which I'm calling x, measured according to new position x new, measured according to x prime. That is, x new is equal to x minus x prime. See, I've just shifted coordinate system to a new coordinate system where I'm describing the position of the thing as x new. If I rearrange this, then I find that x is equal to my new x new, plus x prime. I've just rearranged that around. And if that's true, then x double dot is equal to x new double dot plus x prime double dot. That is the second derivative of x prime. Well, x prime's a constant. X prime's a constant. So the second derivative of x prime is 0. So I'm going to make these substitutions in my differential equation here. That is, x double dot is equal to x new double dot plus 0. I made that substitution for x double dot. Plus k over m times x. Well, x is x new plus x prime, which is mg over k, is equal to g. So I just made this transformation of coordinate, made the substitution. Look at the beautiful thing that happens. Of course, x new double dot just has 0 added to it. That doesn't do anything. When I multiply through k over m, I get k over m times x new plus k over m times mg over k, which is g. I can now subtract g from both sides of the equation, and look what I have. X new double dot plus k over m x new is equal to 0. Now it is harmonic oscillation. Now that was all a bunch of mathematical rigmarole to prove a very simple idea, which is this. In vertical harmonic oscillation, or indeed in any situation where a harmonic oscillator is subject to a constant external force, because gravitational force is constant, when a harmonic oscillator is subject to a constant external force, it does not oscillate around the equilibrium position. It oscillates around the shifted equilibrium. So adding the mass to the vertical oscillator effectively shifts the system down to a new equilibrium, and it oscillates about that new equilibrium, which means the vertical harmonic oscillator and the horizontal harmonic oscillator have solutions of the same type.